Okay, welcome back. This is Mr. Hassan's Maths channel, and in this question I'm going to be answering a question here about functions, and this question is from the October-November 2019 Cambridge Paper 1 Variant 1 of the 9709 International A-Level Cambridge CAIE paper, and this is also question number 2, which I have put in my end of topic worksheet on functions, inverse and composite functions for this is for my end of topic worksheet number 5 for my P1 collection of worksheets, and one of the students has asked me to answer this question, so I'm going to do so. So it says the functions f and g are defined by f of x is 3 over 2x plus 1. Now sometimes this is written in this form, and most often it's written like this. They mean the same thing, so don't worry. Okay, so these two can be used interchangeably. This just means f is such that x maps to 3 over 2x plus 1, x is greater than 0, and this part here is very important. These parts at the end, okay, which state the domain of the function, are really important. So this would be written as g of x equals 1 over x plus 2. Okay, 1 over x and then plus 2. And again, x is greater than 0 is the domain of this function. Okay, so I'm going to answer this question not like just writing down what's in the mark scheme. I'm going to try to explain the question in a bit more detail, and I'm going to also maybe add a few bits to the question which reflect some of the types of things that are being asked in more recent papers, to make it a bit more beneficial. As I said, these videos are really primarily designed for me to help my own students in school, and sometimes I address issues that I have in my mind about what type of questions students have been asking me. So I might sometimes go into some detail on certain points, okay, which some of you who are just looking for a talking mark scheme might not really be looking for. So, you know, please be warned that this is not just going through like a walkthrough of a paper. It's a teaching tool that I use to explain things to my students, and then I just share it on YouTube anyway, so whoever may benefit can benefit. Okay, so my point is not to like target an audience and get views and all that kind of stuff. My aim is to teach my own students and you know, address issues that I see with them, and if other people can benefit from them, that's fine as well. All right, so now we're asked here to find the range of function f and the range of g. Now, when we're asked to find the range of a function, we have to understand what the word range means. Now, the range of a function basically is what can come out of a function. You have the domain and you have the range. Okay, you have the domain and you have the range. Okay, so the domain is whatever goes into the function. Okay, so the domain is what goes into the function, and the range is what comes out of the function. Okay, that's the output. Okay, so let's put it like this. This is the function itself. Okay, so this is the function, and the domain are the values that go in. So they're the x values that can go in, and the range are the values that come out. So they're the values of y that can come out. Okay, and so whatever goes in here, it basically goes through the function rule, whatever it is, the operation, and whatever comes out is the range. So we got to find the range of this function given that this is the domain. Now the domain is a set of values which is continuous from x is greater than 0, means from x is from just over 0 all the way to infinity. All the numbers that exist, okay, is what can go into both of these functions. Okay, if the domain was a particular value, supposing they say the domain is x equals 1, then we could only put 1 in here, and the range would only be one value, whatever comes out when x equals 1. What happens when x equals 1? You're going to get 3 over 3, which is also going to be 1. So when x equals 1, y would be 1. That would be the domain, and that would be the range. There would only be one, basically, value that comes out. But here we have a whole range of values from greater than 0 all the way to infinity. That's what can go in. Okay, so that's the things that can go into the function. And we've got to work out what comes out of the function. Okay, and the range, okay, represents what can come out with this particular domain and this particular rule. Okay, so that's what we have to work out. What is the range of this function? And a very efficient way of working out the range of any type of function is to picture what the function looks like. especially of the type of functions that we know its general shape. So when we see a function like f of x equals 3 over 2x plus 1, we have to ask ourselves, what type of function is this? What does it look like when you draw it? Like, you have linear functions which give straight lines, you have quadratic functions which gives like this type of smiley or frowny faces and have maximum minimum points. You have cubic functions which kind of go up, down, up again. You have reciprocal functions which have things which are called asymptotes, which they never touch. You have exponential functions which just keep on rising and rising depending on the curve. So you have different types of functions that you have to be able to match. What shape is this going to have? And you know, this is a function which has x in the denominator. Anytime you have an x in the denominator, you're going to have something that has this type of reciprocal function look to it. It's going to have asymptotes, lines that it never touches. So if I was to draw this first without any restriction, just to give an idea of what it looks like, then it would basically be a straight, a reciprocal curve. So I'm going to draw my pair of axes, and I'm going to, you know, think about what this would look like. So when you have a reciprocal function, you think, all right, it has asymptotes. Okay, so let's write it as y equals 3 over 2x plus 1. Now the first thing you should realize with these reciprocal functions, the denominator can never be 0. So here the denominator will be 0 when 2x plus 1 equals 0. So when x equals negative a half. So x can never equal, you can't ever have an input into this function where x is equal to negative a half. So x equals negative a half is straight away going to be an asymptote. Okay, if we were able to draw this function completely, but of course we're not going to be able to because it's got a restricted domain. But I'm ignoring the domain first just to give an idea of what the graphs would look like. So that's going to be the asymptote, or one of the asymptotes. You also always have a horizontal asymptote, okay, and that's going to be basically when the denominator here, if you swap these two, the denominator is going to become like y, and if the denominator becomes y, if you basically swap these two around and put this in the denominator, you're going to end up with 2x plus 1 equals 3 over y. Now y can't be 0 either. Okay, another way you can think about it, if you put y equals 0 and try to solve the equation, it will be something that gives you a contradiction, because if you put y equals 0 here, you'll have 0 equals 3, which is a contradiction. So y cannot be equal to 0. So y can't be 0 and x can't be negative a half, which means those are the two asymptotes. So I'm going to draw another line here to represent the asymptote y equals 0. Okay, and I know that this graph its parent function looks like this, y equals 1 over x. That's how it normally looks. So I'm assuming it's going to be on these two sides that the graph will be, but we can be sure of that by finding where it crosses the y-axis. Now it crosses the y-axis when x equals 0, and we can see when x equals 0, y is going to be 3 over, that's going to be 1, which is 3. So y equals 3. So it's going to cross the y-axis somewhere over here. So that means the graph must go something like this. So that's going to be where it crosses the y-axis at 3. And then the other part of the graph will be on this side if it's unrestricted. So we can see that this side will continue on, this side would continue on, and this side would continue on, and this side would continue on. Okay, and that's how it would look if there was no restriction. So if there was no restriction to the domain of f of x, the only restriction would be that x can't be equal to negative a half. That would have to be stated. And then the range would be all the values of y except for this one value. So the domain would be y is an element of all real numbers, but y cannot equal 0. However, that's not the case here. The reason is the domain of our graph has been limited to only x values which are greater than 0, as we see from the question. And that's going to make a huge difference to this graph and to the answer. So what we're going to do now is we have to get rid of any part of the graph where x is less than or equal to 0. So I have to get rid of all of this section here. So that section doesn't exist anymore. And I've got to get rid of all of this section here up to 3, including 3 itself. So I'm going to then draw here a open circle at this point to show that the 3 is not included, but just everything slightly more than 3 is included. So now our graph of our function, this is our graph y equals f of x as defined by this statement here. So we have 3 over 2x plus 1, where x is greater than 0. This is where this graph exists. So there's no output of this graph which is beyond this region here. Okay, so if you think about what the output or the y values that can come out of this are, they're no more than the values of y between those. The output will always be between greater than 0 and less than 3. There will be no values up here because the values of x less than 0 have been taken out. So no values over here. There will be no values on this side going down. There will be no negative values. The range of this function, therefore, the range of f of x, okay, of f of x is therefore going to be given by the values of y, which are between 0 and 3. You can write it as the values of f of x between 0 and 3. Both of those are acceptable ways of writing it. But don't put x here. You don't put x for the range, and you don't put y for the domain. You put for the range, you put y or the name of the function, which we called f of x here. So there's the answer to part 1 of this question. Okay, so it's very important for us to understand what the graph looks like and how to, deal with it when you have restricted the domain. Now, g of x has a similar type of graph in the sense that you have a reciprocal graph. Maybe a bit easier to draw because it's like a straight transformation of this graph. You have to just take this graph and raise it. Actually, it's plus 2. Don't want to make silly mistakes there. Okay, it's 1 over x plus 2. So it's just been raised by 2 units vertically. Okay, so I'm going to make a little sketch again. When you do a sketch, it's always nice to make it neat. Use a ruler to draw your axes and try and be as neat as you can. So we're going to have y, that's the x-axis, that's the y-axis. In this case, I'm going to draw the original, all right? And then I'm going to draw the, let me make a different color, make it different. So I've got this is be y equals 1 over x. That's what I'm going to draw now. There will be my 2 asymptotes, and the graph would look like this. This would be y equals 1 over x. That's what I'm drawing first. Okay, that's what it would look like, 1 over x. Okay, now what I'm going to do is, I'm going to, let me choose that. Let me group these together. Will it work? Yeah. So basically what's going to happen is this whole thing is like a translation of 2 units upwards. 2 is added to the whole function. So all the y coordinates are raised by 2. All the x coordinates, they stay as they are. So it just raises vertically by 2 units. So it's going to go something like this. Okay, that's how it would look now. Right, so that will be your y-axis. Let me bring this asymptote down a bit now. Oops. Okay, can't move that. Yeah, that's fine. All right, so now your asymptote here is still x equals 0, but the asymptote now becomes y equals 2. Right, and this is how your graph will look. So this is the graph of y equals 1 over x plus 2. All right. This is the origin. Now this graph is not going to cross the y-axis but across the x-axis here. So where does it cross the x-axis when y equals 0? So you have 1 over x plus 2 equals 0. Negative 2 equals 1 over x. If you make x the subject, you'll have x equals negative a half. So that's going to be negative a half. All right, now we don't actually need that now. Why? Because our domain is x is greater than 0. Okay, so if we think about how the graph would look, supposing there was no restriction on the domain, then it will be, the range would be all real values of y except for y equals 2. But because now we have to get rid of all of this section of the graph, this all has to go, we're only left with this part over here. Now in this case, this side is going to get closer and closer to 2 without reaching it. But this side is going to keep going up and up and up, going to get closer and closer to x equals 0 without ever reaching it. It's going to go up to infinity. So basically, we can see here our range is y is greater than 2, not equal to 2. Why? Because this is an asymptote, we'll never reach it, and it goes up forever. So here we can say the range of this function is g of x is greater than 2. You can write y, you can write g of x, but you can't write x for the range. So there's the answer to this second part of the question, part 1. So we've got the range of both of the functions. F of x is between 0 and 3, and g of x is greater than 2. Okay, so that concludes part 1. Now we're going to go into part 2. It says find an expression for f of g of x, giving your answer in the form ax over bx plus c. So we got to find f of g of x. So basically g of x has to go into the function f. Okay, that's what we have to do. We have to put function g of x into function x. So this function, this has to replace the x in this function f. Alright, so what you have to do is like 3 over, and you're going to put this whole thing into there. So it'll be 2 times 1 over x plus 2, and then plus 1. Okay, so you're taking this and replacing the x over there by it. So you have 3 over 2 times x. X now becomes 1 over x plus 2, close the bracket, plus 1. Okay, that's inverse the composite function f of g of x. Now, this looks of course a bit messy. We have to make it look like that. Now what I would do here is I would just write this as 3 divided by, just to make it less complicated looking. Having fractions over fractions is a bit messy, so I have 3 divided by, and the other thing I would do is I would take this and make it into one fraction. So let's do that on the side. 1 over x plus 2. If you make it into one fraction, you have to have the same denominator, so 1 over x plus 2x over x. So this 2 becomes 2x over x, so you can then add it together with this. So you end up with 2x plus 1 over x, 1 plus 2x, or we can say 2x plus 1 over x. I wrote it like that because I see the answer is like this here, so it's probably going to have something similar to that. So you're going to have 3 divided by, and you're going to have 2 times. Now, instead of 1 over x plus 2, I'll write this as 2x plus 1 over x. And then plus 1. Now, I can continue here. So we have 3 divided by, whoops, what happened there? Sorry. Bit of a mess there. So 3. So 3 divided by, and this is going to be 2 times 2x, which is 4x, and 2 times 1, which is 2, over x plus 1. And again, what I can do is I can actually get this ready from now to make it into one fraction. So this 1 over here, I'm going to put plus x over x. So I can make it to one fraction. So I have 3 divided by, and you're going to have 4x plus x, because they're under one denominator now, which is all x. So there will be 4x plus x, which is 5x plus 2 over x. And now the final step here is to basically just use your KCF. So the 3 stays as it is. This becomes multiplication, and you're left with x over 5x plus 2. So this is, remember, 3 over 1 times x over 5x plus 2, which gives you 3x over 5x plus 2. So f of g of x is 3x over 5x plus 2. Now the question asked us to find an expression for f of g of x. Okay, so that's where we stop. The question could have said find f of g of x. If it just said find f of g of x, then you would have had to state the domain of f of g of x. Okay, you would have had to state the domain of f of g of x. Right? If it just says find f of g of x, it means find the expression and the domain. The domain is part of the function. You must mention it. All right? And so, especially if the domains have some restrictions to them of the original functions, if the question says find f of g of x without mentioning just expression, you would have to give its domain. And sometimes they would ask you to give a reason why the function f of g of x exists. Okay, so sometimes a composite function of two functions cannot actually be made because of certain restrictions in the domain and the range. Algebraically, you might be able to write them out, but they won't actually exist according to the values of the domain. And so I'm just going to explain that, even though this is not part of the question, because that's one of the types of questions that are being asked more and more commonly in the later papers. So for example, if the question says, you know, does f of g of x exist? Then it could say, or give a reason why f of g of x exists. So basically what we can see here is g of x has to go into the function f, as we see from this. Now, if the range of g of x, if the output of g of x, and we know that the output of g of x was g of x is greater than 2 from what we just did in part 1. Okay, if the output of g of x does not fit completely within the input of f of x, then the function won't exist. In this case, it does exist because the output of g of x are values which are greater than 2. So values that are greater than 2 will fit into this domain. Any value greater than 2 will end up being able to go into this domain. So what comes out of g of x are values which are greater than 2. What can fit into f of x is all values of x which are greater than 0. That means that will fit into it. So g of x fits completely into f of x. The range of g of x is, completely fits within the domain of f of x. Therefore, the function f of g of x does exist. Okay, so they might ask you that question. All right, very important for you to understand how to deal with such a question. Now, next part of the question says, find an expression for the inverse of f of g of x, giving your answer in the same form as in part 2. So in this kind of one fraction form. So we know that f of g of x, the original function that we just found, is equal to 3x over 5x plus 2. And we want to find the inverse function. So we are going to find the function that basically undoes this function. To find the inverse function, the first step is for you to call the original function y, and you have 3x over 5x plus 2. And then at this stage, I like to, at this stage, swap the x and y around. So I'll write y as x, and I'll write x as y. So wherever I see x, I call it y. Wherever I see y, I call it x. And now when I make y the subject of this, I will have got the expression for the inverse function. So I'm going to now make y the subject. So I'll first multiply both sides by 5y plus 2. And then I'll expand the bracket. So I'll have 5xy plus 2x equals 3y. Now remember, we want to make y the subject. So what I would do here myself, and many people might do the opposite, but what I would do is I would keep the 2x on this side so it stays a positive term, and I would subtract 5xy from both sides. Okay, now I brought the y's together. We want to try and make y the subject, so I brought y's on the same side of the equation, and now I'm going to take y as a common factor, so I only end up with one y term. So y times 3 minus 5x equals 2x, and then finally we can just divide both sides by 3 minus 5x, so we end up with y. So we have 2x over 3 minus 5x equals y. So therefore the expression for the inverse of this function is going to be given by 2x over 3 minus 5x. That's for the inverse of fg, sorry, not fg. Okay, so there's the answer to this question. Okay, and that's fine. Now some people, as I said, might have gone a different route after this stage. So I'm going to take it from this stage, and if you got this, it's still correct. Some people would have said, okay, let's bring the y's together. So you have 5xy minus 3y, and then you have to subtract 2x from both sides. Take y as common, so you have 5x minus 3 equals negative 2x. So y equals negative 2x over 5x minus 3. So you can see that they look slightly different, but they're actually the same thing. If I multiplied both the numerator and the denominator of this by the same thing in negative 1, I will get exactly the same thing as this. So they're the same, it's just written differently. I just don't like having a minus sign sticking out here. So I basically decided to keep that 2x term positive, subtract 5x from both sides, and then proceed. But this is correct and this is correct. So your answer in the end is the inverse of f of g of x. Inverse of f of g of x. So you have f of g of x. Okay, and there's the answer to this question, and that completes the whole of the question. And that's basically the question done. All right. So other questions from this particular paper can be found in the playlist, which will be appearing over here for this paper. For answer other questions from this paper. Other questions from this end of topic worksheet can be found in the playlist that will appear over here in this part of the screen. You can watch other questions dealing with functions in general from my Cambridge P1 collection in the playlist in this section here, and you can subscribe to my channel by clicking on this link. Thank you for watching. See you soon.